Good day to you. My name is Nazariy, and today I want to present my master thesis with the title Parameterizing Human Speech Generation. This thesis was done under the supervision of Diego Saez-Tramper. And I would like to start with the definition of the problem, of text-to-speech problem. The most core definition of TTS is a process of mapping of written text to the audio of human speech. So the motivation behind solving this task are huge. The most striking one is making computer systems socially acceptable. And we can see in the field that the main state-of-the-art solutions are proposed by companies like Google or DeepMind, and they are successfully integrating their solutions in the services like Google Maps or Cortana. The other ways to use the models are converting of written books to audio format, voice acting in movies, dubbing of movies without human actor. The research questions that we try to answer are the following. Whether is it possible to build a state-of-the-art closed system with limited computational resources? Also, we ask ourselves how we can parameterize speech synthesis by different elements of the speech, like melodic component, prosody component, voice of the speaker, and so on. Also, we needed to evaluate the system because the task is complex in its nature. So the evaluation of TTS systems, basically, the main two properties are naturalness of generated audio and intelligibility. Naturalness corresponds to the factor how good the model mimics the way the human speaks, and intelligibility corresponds to the question whether we can understand what it's producing. Most of the paper use mean opinion score metric to evaluate the models. Basically, it's just an average of scores collected from different human scorers, and usually the scale is from 1 to 5, and you can see the meaning behind each of the scores. So in 2016, Google researchers presented arguably the most significant paper on the topic. They introduced the WaveNet architecture, in which they basically built conditional model of the sound of human speech. So it basically works like language models for speech, for text, and they modeled gen probability of raw audio value by the product of conditional probabilities. They were highly inspired by the paper of other Google researchers in which they introduced Pixel CNN, which was used for generation of natural images, and they applied the same architecture to 1D space of audio. So basically, the main idea was that they used, so the main problem with building the model on the raw audio is a high sampling rate. So, for example, on the raw audio for 1 second, there are usually more than 40,000 of values. And they use dilated convolutions to exponentially increase reception field of the network by linearly increasing the amount of trainable parameters. The next, and the results. WaveNet outperformed significantly all of the state-of-the-art solutions, and they narrowed the gap between model-generated audio and human recorded speech. The next big breakthrough happened by introducing of Take-O-Tron model, which was also published by Google researchers, and the main idea was to separate two tasks. On the first stage, they generated null spectrogram, and on the second stage, they produced the audio based on null spectrogram. For vocoding part, for producing of the audio, they used modified WaveNet architecture, and they introduced this Take-O-Tron model to generate null spectrogram. Also, I need to mention the results of Take-O-Tron. They narrowed the gap between original human speech and model speech to almost statistically insignificant one. And currently, this is the state-of-the-art solution for text-to-speech systems. Also, I need to mention another work by Google researchers in which they introduced generalized end-to-end loss for speaker verification. They tackled the problem of speaker classification from clustering point of view, so to say. So they learned the embedding of the speakers and emphasized utterances that were incorrectly predicted. Basically, they built similarity matrix for each of the embedding and tried to find the centroid which is closest to each utterance of the speaker. Then later that year, Google combined all of the three papers in the transfer learning for multi-speaker TTS. Basically, they parameterized the tecotron by the speaker embedder, which I mentioned in the previous slide. And they were able to produce audio customized by voice of the speaker. They evaluated the model by two metrics, naturalness and similarity. They used a huge internal data set and they achieved 3.03 in most score for similarity metrics. Also, I need to mention Viber-NN, which was motivated by the idea to make vocoder part more computationally efficient. And they basically replaced the weighted convolutions with gated rectified units. And you can see that with the increase of hidden state of the model, the most score is getting closer to WaveNet most score. Initial proposed method. So we wanted to test the hypothesis that we can parameterize the audio not only by voice embedding, but also by sentiment, emotion embedding of the speaker. We wanted to use parameterized tecotron by two embedding vectors, and then we wanted to replace WaveNet from the original architecture and use Viber-NN to, because it basically is simple to train and to work with. Challenges that we faced. First one was to build the model with no published code or specification, because generally speaking, Google published their papers with the main core ideas, but does not provide size of the model or does not provide source code for the models. Also needed to train the model with limited computational resources once again. We needed to build evaluation framework to evaluate our results. And the hardest task was to find data set with annotated emotions, because text-to-speech problem is supervised problem. And to train simple text-to-speech, we need transcription to each audio sample. To parameterize it by voice, we need annotated voices. And to parameterize it by emotion, we need annotated emotions. So we found data sets with an annotated voice and transcript of the text, but we didn't find the data, and there is no openly available data set for with the labels of emotion. The natural solution that we wanted to implement to tackle this problem was to use state-of-the-art emotion classifier and apply it on already existing data set. But unfortunately, state-of-the-art emotion classifiers are not very good, and usually they provide, so we found only one open source implementation with accuracy more than 70%. So we decided to train our emotion classifier. We successfully trained it, but when we labeled the data set, we received highly unbalanced distribution of emotions. So more than 90% of the emotions were neutral. So we decided to separate our proposed method. We decided to build a text-to-speech system with parameterization by voice of the speaker. And also we decided to tackle classification of emotions by applying the same thing that Google researchers did to voice classification. Here you can see data sets that we used, and I won't go into the details, into the detailed description of them, but you can see two outliers: LG speech dataset with only 24 hours of speech, and raw DES speech dataset with only 2 hours of speech. So LG speech dataset was used for debugging purposes and to iterate quickly between different models. And raw DES speech, so it was used for the sentiment classifier that we used as a baseline model. And that's why we used this dataset to reproduce their experiments in the most precise fashion. So basically, also we used Viber NAN implementation for the vocoding part. We used pre-trained version on LG speech dataset, and we trained it further on the datasets that we used for our models. Also, we started with Tacotron implementation with Griffith-Lane vocoder, and this was the initial point. This is the baseline result that we compared to, and this is this was the start for our developing, which later we parameterized this Tacotron model by voice embedding. We built the evaluation framework. Basically, we needed to evaluate three things. First one was to evaluate how good the generated speech is. And second was how similar to the voice of the speaker our output samples are. And also we needed to evaluate how good our sentiment classifier is. So here on the screen you can see screenshot of UI for text-to-speech estimation. Also you can see the link, and you can actually listen to the samples anytime that you want. Also here is the link, the screenshot of UI for scoring of similarity of voices. And so we obtained TTS results. We collected 5,000 scores from approximately 200 people. We outperformed baseline model by mean opinion score of 1.6. We divided generated samples in two categories, female voice and male voice, because usually in the literature, authors mentioned that there is, it's harder to generate male voice due to the low frequencies. Our mean opinion score is reasonably good, but it didn't achieve like score of 4. And the reason to this can be that usually this text-to-speech systems are evaluated on very short sentences. And we try to evaluate the model also on the longer one. For example, you can see over here that there are 4 samples. And let me actually show you the results. This is the result of baseline model.
Act on these orders with great speed.
And this is the result of our model.
Act on these orders with great speed.
For the longer samples, actually the rhythm and the prosody was increased. So for example, baseline model generated
I'm the lizard king, I can do anything. We came down the rivers, highways, we came down from forests and falls.
And our model generated this.
I'm the lizard king, I can do anything. We came down the rivers and highways. We came down from forests and falls.
Yeah, so we can see that the tempo of the speech is increased due to the length of the sample. Also, we evaluated voice parameterization. We collected 400 scores from 50 people. We divided our generated samples by the lengths of the initial sample that we used for embedding by 3, 5, and 8 seconds. We achieved maximum mean opinion score was 2.77. And actually it is relatable to the to the one published in the Google paper, where they achieved a similarity score of 3.01. And yeah, and also we tried to evaluate our model with real life scenarios, close to real life. So, for example, this is the complexity was so it's hard to evaluate how similar the voice is because our model does not copy the emotion of the speaker, original emotion of the speaker, and also our model is saying one standard sentences for each voice. So here are the results for male copying of voice with no noise.
Hello, everyone, and welcome back to the coverage of the World Blitz Championship. It's the ending.
And this is the result that our model generated.
It rhymes with lead and red rhymes with lead, but rate and lead don't rhyme, and neither do read and lead.
So it's monotonic, and that's why it's hard to compare it to the original voice. And this is the example with slight noise without any initial preprocessing of the audio.
This is all wrong. I shouldn't be up here.
Yeah, and this is the result generated by our model.
Red rhymes with lead, but red and lead don't rhyme. Neither do red and lead.
So you can hear that actually the noise in the initial sample affected the results. And yeah, that's it. So for sentiment classification evaluation, we used more conventional metrics. So here you can see the table with precision recall a font score by all the classes present in the dataset. Yes, we achieved weighted average of 0.83, and we outperformed baseline model by 0.1. Basically, our data set is too small to say that it will generalize well and outperform state-of-the-art solutions. But we believe that we didn't find any implementation of such an approach for classification, and we believe that it will generalize. Yeah. So also, I want to thank for the recension from Grant Reber because it was highly valuable and useful to read the comments from pioneer in the field. And the one comments that I want to address are that quality of voice cloning. Actually, I want to emphasize that the evaluation was on the voices not present in the dataset, and actually we used and we achieved similar scores to the one presented in the original paper. Actually, maybe they are too high because I believe that some of my relatives were evaluating the models, and maybe this affected the score. But and also, like standard deviation is much higher for these scores because a lot less scores were collected. Also, reasoning behind WaveNet with WaveRNN, basically Grant said that if I could train Tacotron, that I could train WaveNet too. Yes, that's true, but so I had limited computational resources, for which I want to thank to Dmitry Spodorets from VTech Lab. And basically, I used these resources to train parameterized Tacotron. And I didn't, so yeah, and I wanted to use something simpler for WaveRNN training. And that's why I took open source implementation with hidden state of 300 and with the size of the hidden state. Also about no included audio samples, I included the link to the estimation web solution. So I couldn't include it into the PDF itself, but I tried to fix this during my presentation today. And conclusion. So in conclusion, we built the TTS system with the ability to parameterize speech generation by voice in real time. We developed an evaluation framework for the subjective estimation, which can be used to estimate all kinds of subjective results. We improved the quality of baseline model, showed that approach for voice embedding can be used in sentiment classification problem, and we built the emotion classifier, which performs on the level of state-of-the-art classifiers, but we used much smaller data set, and yeah, so it's not quite quite relatable result. So I want to thank you for your attention, and I will gladly answer all of your questions.
Would you be glad to ask a question first? Yes, just a very quick question because like the structure of this work. So I mean, it's still a puzzle how speech generation very much connected with the emotional recognition. So it seems like it is connected science.
So basically, the idea was that so the approach that Google took for this, they learned the embedding of voices. They learned this vector of 256, and basically, by this vectors, we can perform classification, and they had very good results with this approach. And our hypothesis was that if we do the same for sentiments, if we train this meaningful embeddings and parameterize Takatron model by them, then we will be able also to parameterize by emotion. But because we didn't have like this whole data set with everything annotated, we localized it to sentiment classification, and we assumed that if we can build a good sentiment classifier, then it should be reproducible on sentiment parameterization by this embedding. I hope that I answered the question.
More questions? Gentlemen? Yes.
Did I understand correctly that you confessed that you wrote the results?
No, I didn't.
So, but you said that some of your relatives.
It was unintentional, and I still don't know whether it was. So there is uncertainty. I corrupted and didn't corrupt at the same time, because I don't know who answered.
I wonder why you did not show standard deviations. And we assume that you did that on purpose.
No, actually, I wanted to do so, but I forgot about it, and I didn't include this into the text.
It was unintentional.
Honestly, and I wanted to keep this way of presenting the result in the presentation as in work. So
yes, the first question which arises straightforwardly, I have written it. Where are the standard deviations?
Yeah. So
before you confessed.
That's good that I confessed.
Oh yes. Yes.
Так, я перемішую, тому що я використовував. Так, я відповім, але з преамбулою трішки, тобто ми оцінювали на 50 реченнях, і речення були сконструйовані з Harvard Sentences і з всяких популярних в поп-культурі речей. І ми помітили, що люди зазвичай не оцінюють ці 50 семплів, тому ми перемішували, власне, самі речення, щоб не отримати результати на одному і тому самому реченні весь час. На рахунок семплів, пізніше ми почали, але це не дуже мало сенсу, тому що бейслайн, він продюсив набагато гірші результати, і, в принципі, якби ми перемішували чи не перемішували, в принципі, люди все одно би зрозуміли деяка модель, скажімо так. І, в результаті ми це забрали.
На якісь ітерації ти вже людина починає оцінювати, а просто починає.
Ні, я проходив там. Тобто ти розумієш, для чого це робиться, і намагаєшся. Але тут питання ти намагаєшся цього.
Так, і в принципі суть в тому, що...
Ще одне зізнання.
І суть в тому, що я це опублікував, так би мовити, в середовищі своїх соціальних контактів, і в основному вони не є native speakers. Тобто в основному це люди, які використовують англійську як другу мову, того це теж могло, тому теж результати можуть бути не до кінця коректні, тому що це зроблено не native speaker.
Маєте на увазі оцінку?
Так. Так, тому що в основному це оцінювали українці, у нас було...
Тобто вони мають мати слух, а не знання англійської. Ви ж не прохали говорити щось.
Так, це правда.
Вони просто слухали, оцінювали схожість.
Так, в цьому випадку оцінювали якість, а в цьому випадку оцінювали схожість.
Як я зрозумів з вашої роботи, будь-що робить запис голосу не монотонним, ви називали словом emotions. І очевидно, що розпізнавання emotions – це дуже складна річ навіть для багатьох людей. І я хотів зрозуміти, чи ви справді намагалися виокремити якраз різні фактори, які можуть впливати на зміну голосу. Я не маю на увазі emotions, там, наприклад, акценти, де людина виросла, чи там якась людина говорить з більшою кількістю пауз, якась швидше. Чи додавало якийсь контекст beside emotions?
Так, насправді ми пробували передати ритмічний компонент, але у нас не вдалося. Одним словом, ми не встигли це включити в тези, але ми, власне, не ставили такої мети. Власне, класифікація емоцій – це складне завдання, і от як ви тут бачите, в основному, наприклад, такі емоції, як sad і disgust, вони конф'юзили наш класифаєр. У мене є візуалізації того, як ми тренували. Візуалізації цих ембедінгів. Тобто, це те, що ми отримали після 110-ї епохи. І, власне, після 410-ї ми отримували такі в основному результати. Тобто, воно виділило окремі кластери, але деякі воно не могло виділити, і все одно вони мали певний оверлеп. Власне, це було зроблено не без поділу на трейн і тест, тому що для навчання ембедінгів, власне, нам не треба було якихось таких конкретних метрик, ми просто хотіли оцінити це все. І просто ми не могли знайти по емоціях, і я просто вирішив використати архітектуру для навчити ембедінги для емоцій на тому датасеті, який я мав. І отримавши вже, власне, ці результати, ми, зробили переміщення і акцент на розпізнавання емоцій.
Питання там одна з цілей це було про limited resources. Як ви визначаєте обмежені ресурси?
Так. Власне, ми базуємося на твердженні, що в світі є 4-5 компаній, які мають, може більше, до 10 сотні компаній, які мають ресурси, які використовують Google і DeepMind. І, відповідно, ми не відносимося до тих людей, і того ми, власне, кого б не порівняти з ними, у всіх будуть limited computational resources. Тобто я вдячний за те, що мені надали доступ до GPU на клауді, але, власне, все одно це доволі локальний ресерч, і нема таких...
Скільки ви витратили ресурсів? Як довго то все тренувалося? Там була одна GPU, так?
Там в мене був кредит, відповідно, я міг наконфігурити різні інстанси з різною кількістю GPU. Такотрон я тренував дуже довго, тобто я ітерував локально спочатку на своїй меншій, зменшуючи кількість, розмір самої сітки. Потім в мене була трохи проблема, тому що я не міг зрозуміти, як використовувати Cloud GPU, і ми використовували всякі такі скрипти, які дозволяють на Google Colab тренувати довше, ніж він дозволяє. Потім ми отримали, власне, оцю GPU, ми зрозуміли, як працювати з клаудом, і, власне, Текотрон ми тренували суто на клауді вже останню версію. Самі ембедінги для сентименту це дуже просто, і локально наше GPU справлялося. Для voice ембедінгу ми теж, ми не могли це.
Думаю, в наступні цей маємо ставити досягнення з contribution. DevOps. Добре. За межами цього корпусу.
Напевно. Тоді це все чи що?
Ні. Це все. Це крім мене. Все. Добре. I have a formal question for you. Therefore, in a formal language. Why still title of your thesis? Sorry for the formality at the end.
Parameterizing?
I corrected your title several times, and you still have "of" in the title of your thesis.
Yeah, that's right, but...
That's wrong. I do understand there is Spanish influence. Well, you are not Spanish.
I see. I hope that I can fix it, and actually I found other mistakes, for example, for evaluation. For the evaluation, we stated in the work that we had like 100 people, but actually we had 200. And
so you have to resubmit the final shape, right?
Yeah, I will work through and correct everything.
Will you be allowed to?
I hope so. I hope.
Let's go for better, because otherwise you will still have "of" in the title. I do understand that you don't care that you're Spanish oriented, but anyhow. My second formal question is, the goal of your thesis project was, and I'm citing, implementing something.
Right.
Right. Was it a software development project? Wasn't it a research project?
Yeah, we implemented the models.
I warned you, that was a formal question. I'm expecting a formal answer.
Yes, we implemented.
So it was not a research project?
It was a research project, but there were a lot of things done.
So as a side dish, you have implemented this stuff, in addition to the research project?
Yeah, and also, yeah. So there are...
It could not be the goal of the project. It could be one of the tasks in the evaluation. So, yeah, the question about deviations has already been discussed as corruption. Yeah, still like that you elaborate a little bit more. Why do you fail on real negative emotions? Was classifier too positive?
They are. So it's hard to distinguish those emotions even for humans. And for example, sad.
Excuses. The humans are not playing the game. You have classifiers. They goes well with the rest of the emotions, with positive emotions, for instance.
Yeah, the thing is that.
Any hints, any ideas about that?
I personally think that to distinguish those two emotions, we need also video input, because the speech itself does not possess all of the features that we need to distinguish them. That's my personal opinion, but it should be tested, my hypothesis.
So, from your future work, I do see that you thought about a different reason. That the data set for learning emotions was insufficient.
Yeah, that's too, no, actually this data set I want to build to build TTS system, text-to-speech system with ability to parameterize. This is the intention behind building of the data set with annotated emotions. Yeah, maybe in other data sets, I will find data sets with better representation and more rich representation of all of the emotions, and it can solve the problem that we faced with these negative emotions.
What do you mean by bullet 3 here? Develop software for models. You have said that it was an implementation project, so you're supposed to have developed it.
Yeah, I have developed, but I want. Yeah, so software is very general word, but in this bullet point, I meant that I want to. Basically, my master thesis will be the base for wider research and for wider product that I want to do, and not yet. But I'm interested because, like, the main idea.
So will be is a little bit of too strong statement, might be.
Yeah, but actually, the idea why I started learning started my education in Supu, because I had like in my mind I had
Potential job offer.
Yeah, potential thing that I wanted to build, and yeah, I decided to apply and to learn all that I need.
Thank you very much. I'm happy with the answers.
Thank you
Especially
too.
about job offer.
All right.
Anything else to ask? Yes. Any questions from public? No. You see, public is still ignorant. You can't work with public. Thank you.